Hey everyone, and today I'm going to go over minimum and maximum values for functions using calculus. You'll also do a little bit of algebra with like quadratics and vertex form, but that's kind of boring, so we're using the calculus method. So first, what is a minimum and a maximum value? And in order to understand minimum and maximum values, I want to bring up critical points first. So a critical point in a function, let's say we have some function f of x. A critical point is when this function's derivative, so f prime of x, is either equal to 0, meaning we take the derivative and evaluate it and it gets, 0, or it's undefined. So what this kind of looks like is, let's say we have an axis here. We got like, that's an awful looking polynomial. So we got something like the sine wave or something, right? We look at, looking at this graph, right? We can pretty easily eyeball a minimum value here. Probably should have used a different color for that, but yeah, let's do that. We'll do red. A minimum value here because it's the lowest point on our graph. And not only that, we can sort of visualize the tangent line for it, meaning, it's like a straight line. That's what it means by the derivative being 0. At the same time, we can also visualize a maximum point in this. Where's my cursor? Oh, here it is. This maximum point here also seemingly has a tangent line that is near straight, meaning its derivative would also be 0. However, if we had a function like this and then went up, immediately went back down, this maximum point here, we can't tell if the tangent line is straight because it goes up and then it goes immediately back down, whereas these, they sort of taper off a little bit before they start changing their derivatives. So this one would be a case where the derivative in this case is undefined. We'll just say undef. So this is undefined. And so these points here are all critical points. We see that our tangent is evaluated and it gets 0 or undefined, and that's the criteria for it to be a critical point. So every minimum and maximum value is a critical point, but not every critical point is a minimum or maximum value. I think that's how it works. Don't quote me on that, but it's hopefully right. So after getting our little bit of intuition for what a minimum and maximum value is, with a little bit of critical points, let's go over finding the minimum and maximum value of a function. So we want the minimum and maximum value of this function. So we have, 3x cubed minus 36x minus 8. Now, in order to find our minimum and maximum values, like I said, we want to evaluate the critical points of the function, which is when the derivatives are 0 or undefined. And in order to find these critical points, we look at the slope. And, the slope for a function whose slope is always changing is its derivative. So we need to first find the derivative of this function, so f prime of x. In this case, we just use power rule, so we have 9x squared minus 36, and the derivative of a constant with respect to x is, 0, so we don't have to include the 8. Now, we want to set this part here to be equal to 0. So we'll say set to find our critical points. So we add 36 to both sides. We get 9x squared. We will do 36. Divide by 9. That cancels out. Divide by 9. We get x squared is equal to 4. Now we take the square root of both sides, but remember, there are no constraints on this function. I never say x has to be positive or x is only negative, so we do plus minus the square root, and we get, I'll write it up here, x equals 2 or x equals -2. Because we're doing plus minus square root, not just the principal square root. So now that we have our values, right? They kind of look like z's, but that's okay. Now that we have our values, we want to essentially analyze our function. So we're gonna do that with a little bit of geometric intuition first. So let's say we have our parabola. We'll say this is not drawn to scale, but this is -36. This is -2, and that is 2. Well, we know our function equals 0 at 2 and -2, meaning those are the roots of our function, and our y-intercept is -36. So, that's kind of our parabola. It's like not aligned. Just imagine they're aligned. So looking at this function, we get a sense of, remember, this is the graph of our derivative, not the graph of the actual function itself. So we're sort of looking at what happens along this derivative in order to determine whether it's a minimum or maximum point. So if we really think about what a minimum and maximum point is, what is it? Well, a maximum point is like the highest point on a graph, meaning that every point to the left, as in less than that, the slope should be positive. It should be rising up to that. And every point after the maximum point, the slope should be negative. It should be decreasing. In the same way, a minimum point, that's the lowest point on a graph. So every point leading up to that should be negative. You're dropping further and further. And every point after that, well, it needs to get higher, because it can't be a minimum point if there's points lower than that. So the slope after that would have to be getting higher and higher. So with this sort of intuition for a minimum and a maximum point, we can look at this graph and we can say, well, over here, right, we have our slope. It's negative, it's going real, we're going up towards this, and eventually, when we go to our minimum point, well, I guess it spoiled it, but going up to here, our slope tapers off at 0, starts to increase, and goes up here. So let's just move this for some space. Now we're gonna like actually evaluate the minimum maximum points. So we take our derivative and we think, okay, we want a point before it and after it to determine what happens to the slope before and after. So we're going to start with 2. We want an x value less than 2 and an x value greater than 2. We can just choose 1. So 9x squared, when we choose 1, well, 1 squared is 1, times 9 is 9. So we have, we have 9 minus 36, and this equals -27. Yeah, okay. And that's at x equals 1. Now let's try 3. That's one higher. So 9x squared when x is 3. 3 squared is 9, times 9 is 81, so we would get 81 minus 36, which is equal to what? Like 45? Right, is that right? Yeah, okay. And that is at x equals 3. So looking at these two things, we see that when we plug in a lower number, our derivative outputs a negative number. Meaning before that, our derivative is negative, it's decreasing. And then we plug in an x greater than 2, so after that point, our slope is now, or our derivative is now positive, meaning it's rising after that. This intuition tells us that at x equals 2, that's our minimum point. Because before that, we're decreasing, and after that, we're increasing. So at 2, that is our absolute minimum point for the function. Now, if we evaluate x equals, or rather, a point less than and greater than x equals -2, so we'll do -3. -3, plugging into that, gets us 9, 81. Yeah, so we'll have, once again, we'll have 81 minus, that's a 4, minus 36, and this gets us 45. And if you plug in -1, well, let's see here. Negative 1 squared is 1 times 9 is 9. So we'll have 9 minus 36, and that gets us negative 27. So this is at x equals negative 3. This is at x equals negative 1. So now when we're looking at this, it's a point less than at less than negative 2, the derivative is positive, meaning it's rising. And at a point greater than negative 2, negative 1, the slope is now less than. It's negative 27, so it's decreasing, telling us that x equals negative 2 is our maximum value. Every point before that is rising up to the maximum value. Every point after that is decreasing to reach our minimum value at 2. So now that we know that, here, let me erase this. No, I can write it. So x equals 2 is our minimum value. So say min, and x equals negative 2 is our maximum value. So now let's just look at what the graph of this function actually looks like. So I'll show it on Desmos after, but I want to draw it first. So obviously it's a cubic because we're cubing, but let's draw our axes here. So we'll have 2 and negative 2. So, I forgot to mention. Okay. Now that we have our minimum, essentially when we have our x values, that's our minimum, where the minimum maximum values take place. But we don't know what the maximum or minimum y value is. That's what determines how high or how low it is. So let me erase the axis and actually evaluate that first. So that's pretty simple. We just plug in 2 into our original function, not our derivative. So plugging in 2 to that, 2 cubed is 8 times 3 is 24, so we have 24 minus 72 minus 8. And this gets us, well, 72 minus 8 is minus 80, so that's what, minus 56. And then we have negative 2, so negative 2 cubed is negative 8 times 3 is negative 24, plus 72 because it's a negative, minus 8. And then I have negative 32, so that's what, positive 40. Is that right? Yep, okay. So now these are our y values. So that's our min y value. That's our maximum y value. So now that we have the intuition, the actual coordinates of these points, now we can draw the axis. I'll draw it down here. I didn't have to make it that large. Whatever. Okay, so 2 and negative 2. So we'll say this is 40, and we'll say this is negative 56. We can draw one dot here and one dot here, and because of the general shape of a cubic, it's going to look something like this, where it hits our minimum point and it's going to go back up. And up until we hit our maximum point, we are still increasing. That is an awfully drawn cubic. Okay. But now let's go to Desmos and actually show what it looks like. So we have y equals x cubed. Wait, no, it's 3x cubed. Plus, what is it? Oh no, it's minus 36x minus 8. So, yeah, I did an awful job drawing, but we can see our maximum point at 40 and our minimum point at presumably negative 56 if I did this right. Yep, negative 56. So if we zoom all the way out, we see our, oh yeah, it looks awful, okay. So we see our maximum minimum values, 56 and 40, and we got a little bit of intuition as to what not only maximum minimum values are, but critical points, which are pretty important in calculus. So yeah, thank you for watching.